So the second to last tutorial will be a mixed online and offline multi-fidelity optimization of experiments guided by simulations. This is very similar to the multitask notebook, and in a fully functioning example, which will need to come at a later date, this gives you some of the building blocks. For the fully functioning example, you'll incorporate the multitask components and splice them into this fourth API that I haven't mentioned yet, which is the scheduler API. And this gives you a lot of flexibility in terms of evaluating things on external systems. In a fully functioning version, ideally this would be able to be running simulations as simulation resources become available. So that could be a Slurm cluster at a university, or Amazon AWS, Google Cloud Computing, you name it. So that's where the simulations would be running as resources are available. And then as experiments are suggested, and then the experimental researchers conduct those experiments by hand and report those back to the algorithm. Essentially, what this does is gives you a framework where you can set up asynchronous optimization on both the simulations and the experiments. So if someone, it basically reduces that idle time and maximizes both the computational and the physical resources in tandem with each other. Now, with that additional configurability comes additional complexity with this scheduler API. And so it's okay if you don't get this on the first go. It might take going through a few times to get how the bits and pieces are going. As it also mentions here, reading through the developer API tutorial and getting familiar with the building blocks, a few of which we've covered here, is important for understanding some of the things here. So the contents of this tutorial will be talking about schedulers and external systems for trial evaluation, setting up this mock external system, which just runs locally, and then setting up an experiment from that, setting up our scheduler class, and then finally running the optimization. And we'll kind of skip over some of the database storage, but talk a little bit about configuring this scheduler and doing some more advanced functionality. So first, an overview of this scheduler, this idea of schedulers. If you're familiar with Slurm, something like the following, or high performance computing at universities, something like the following might be familiar. Otherwise, I'll explain this in some more depth to the best of my knowledge. So we have a scheduler and optimization algorithm that interface with each other, and then we have this external system which has a job queue, a way of receiving jobs, reporting the status of any given job, as well as reporting the results from a job. And so each of these will be interacting with each other, and we'll go through the subcomponents in the Axe framework with the scheduler API that does each of these tasks here. And some of the features of the scheduler API, I talked about some of the configurability, is that you can set concurrency limits for trials that are running in parallel, trials that are running asynchronously. You can keep track of failed trial runs very easily, and oversee the optimization in other ways. If you run these kind of sets of trials or batches of trials, you can get information from those as soon as the individual pieces in the batch are available. And then, like was mentioned, we're going to be using the Axe experiment class. What's mentioned up here. We use a generation strategy, and then, of course, it can also interface with some database backends. And one thing that's cool is you don't have to use SQL if you want to use MongoDB, for example, or some other external database. At the very end of the tutorial, I'll show how you can use this reporting results to an external system. So first, with the mock external execution system. And as I was going through this, I thought, it might be better to skip ahead first to the scheduler class and then move back here. So let's go here to the scheduler class, mostly because we've covered some of the components that go in here. So here we have our scheduler class, and we're going to pass in an experiment, a generation strategy, and then some scheduler options that we can decide on. Our generation strategy comes from this choose generation strategy function, which comes also from our search space. And then our experiment comes from a helper function here where we have our parameters defined using range parameter, our objective, which will come from this mock job metric. We'll go into some more detail about what that contains. And the experiment is based on our a search space, an optimization configuration, and a mock job runner. So the new things here really are the Brandon for mock job metric and the subclasses that make that up, as well as the mock job runner, the other things we've seen in various capacities here. So given that, let's jump back up to the start with setting up a mock external execution system. So we have a trial status class that we'll be using. We have our typical Brandon function and a few helpers with timing and variable typing, which just help with giving nice warnings mostly. So we have our mock job, which is going to represent a job scheduled on our queue. And then our mock job queue client, which represents the job queue itself. And this is where the Act Scheduler will deploy trial evaluations. So this, our mock job has two parameters that'll be associated with it, an ID and then the parameters for that particular job. So each job will get this unique ID assigned to it by the external client, the external system like Slurm or Amazon, wherever, and then it'll also have the parameters associated with the run. So this function here, and each of these are just templates with kind of dummy code, but what actually goes into these functions will be specific to the external system that you're using to evaluate it on. So schedule job with parameters will take the parameters. It will grab a job ID that generally the external system would produce, and it will assign in the dictionary jobs a key value pair with job ID and then the mock job, which will have that job ID and the parameters associated with it. Then we'll have another function which will get the job status at upon request, essentially. And here, for a given job ID, instead of just randomly assigning some trial status, you would use the external system specific code to determine whether that job is completed or it's still running, for example. And then finally, getting the outcome for a completed job. So you, later on, when the scheduler sees that a particular job is completed and you want to obtain the outcome value for that job, you pass the job ID in, or rather the algorithm uses the job ID. And this is also another external system specific code where here, just as a dummy, you're just evaluating the Brandon function, but whatever API you use to get the outcome value. So this is our mock job queue client in order to make sure that we don't generate multiple queues and accidentally confuse them. We're going to, in all caps here, which is just an indicator that this is kind of a constant, we'll have a singleton instance that will return every time. So whenever we call get mock job queue client, it's always going to return this particular instance of the mock job queue client class. So next we'll go into setting up the experiment. and we'll have this mock job runner, which is subclassed with the runner class. And we have a few definitions here. So we have run, which deploys a trial. And essentially this will get our singleton mock job queue. It will schedule a job given the parameters that we decided on and return the job ID for that as a dictionary. And like it says here, it will be attached to the trial as trial.run metadata. Next, we need a function for polling the trial status. So if you pass a set of trials, then you need to be able to check the status for each of those trials. So we'll do a for loop, grab again our singleton, and then for each of those job IDs in the trial that was assigned earlier, that's where this comes into play. Trial.run metadata.get, meaning accessing that dictionary, the job ID parameter, get the job status for that. And what this status dictionary will do is you'll have a dictionary mapping each of the trial statuses, each of the unique trial statuses to the trial indices that correspond to those. So if you have 3 statuses, abandoned, failed, and completed, and, maybe running, then you'll have a dictionary that maps from the abandoned status to the trials that were abandoned and so forth. So next here, that's everything for our mock job runner. Then we're going to make a Brandon metric for this. So we'll subclass the metric class. And for this, this goes back to some of the developer API tutorials and documentation up there mentioned earlier. But we'll need a fetch trial data function, which here will get our singleton mock job queue, and then we'll retrieve our outcome values for completed jobs. So here we'll get the outcome value for a completed job based on the job ID, and this is for a given trial, and then we'll package that up into a dictionary with the trial index, the name of the metric, the name of the arm, our mean value, which is the Brandon float value, and the standard error, which we'll just say is none, or maybe that's something that you specify based on domain knowledge or experiments that you've run, or set to 0 if it's a noiseless function. And then you'll return essentially a data class with the data frame being given by your dictionary there. And if anything goes wrong there, then you'll return an error. So now we're back to the experiment that we created, went over earlier, and the scheduler that came from a generation strategy we specified, and that experiment, noting again that the experiment had our mock job runner and our objective value in our optimization configuration had our custom Brandon metric. So last, or not last, but one of the other things we can do is define a callback function. So as the optimization is progressing, something that we want some other function that we want to call, in this case, visualizing the results via a plot. So we can find this helper function for making the plot and get the callback here. For actually running the optimization, we can run a certain number of trials, pass in our callback, And after looking at the experiment, it'll have 3 trials, since 3 were requested, and you can run that again and get and visualize the updates to it and see that more trials have been added. You can also specify a timeout uh, where if a trial has been running for, or if run end trials has been running for too long, then the operation will just exit gracefully. There's some information for saving things to a SQL database backend, which is really useful if you want to reload the experiment if something goes wrong, if it crashes or gets paused for some reason. Uh, then it makes it very easy to restart it when it's all backed up to the database. Here are some different configurations that can be used for it. So this tolerated trial failure rate, um, the time to live, uh, seconds for the trials. In other words, if they've been running for too long, to mark those as failed, and running trials on batches here, but run trials in batches. And there's some more information about the different scheduler options that you can pass, uh, like a log file path and the uh, amount of information that the logs contain. You can also pass some early stopping strategies where if you can essentially say if an experiment is taking a really long time, for example, but it doesn't seem like it's going to be a very useful experiment or simulation, to cut that off early. Um, and there's some more details about that again in the documentation. I also mentioned the ability to report results to an external system like a MongoDB database, for example. And here, that's where you'll use the scheduler subclass and just define, so you'll subclass the scheduler class, create a new class here, and just define something called report results. And here you can do just about whatever you want in some function, such as write to external database that you define, and then return the optimization success status and optionally a dictionary of outputs. And an example of that dictionary of outputs is given here, where you're subclassing the scheduler again, defining report results, but instead of just returning true and then an empty dictionary, you can report kind of this other information, how many trials there are so far, and then the number of running trials, so on. So that concludes the scheduler method. And like I said, you can plug in some of the elements from the multitask Bayesian optimization. You can plug in some of the components from the multi-fidelity modeling via the custom generation strategies, for example, in order to have this workflow where you're asynchronously running simulations and experiments and utilizing the data that's available to try to most efficiently optimize your problem.